All right, our next speaker is here live. I'd like to present Joe Donoghue. He will be giving a talk on geologic evolution of the Apalachee Bay region, last glacial maximum to present.
After that brief delay, I'm Joe Donoghue, and I want to thank the ARI and Jana and Jack Carswell, and especially Jim Dunbar. Is Jim out there somewhere?
He's downstairs, but he's watching you.
Hi, Jim. I missed Jim last night. I want to thank them for inviting me. My wife and I used to work at Florida State down the road, and we'd come out to Monticello, but not for this. We've never been in the Opera House. This is amazing. So I'm really pleased to be here. Jim asked me to talk about, you can see, about the geologic background of Apalachee Bay, one of the three bays that are being compared and contrasted, and how that geologic basis has affected human habitation. So that's what I want to focus on. I'm going to start with three aspects of the natural system and try and show how sea level is a major driver for all three of these. So the first is the rivers. Here's the three rivers, or really coastal systems, that we're comparing and contrasting. So you just heard about the Chesapeake Bay from Tom Cronin. I want to talk about Apalachee Bay, and then you'll hear about Galveston Bay in a few minutes from Dan Worrell. So Apalachee Bay really is an outlier. It's not an estuary. So the other two are major estuaries, Chesapeake Bay being the largest in the U.S. Apalachee Bay really is a coastal embayment, not an estuary, because it doesn't get enough fresh water to qualify as an estuary. It's also smaller by about half, 14,000 square mile watershed versus about double for each of the other two. So first of the three aspects that I want to focus on is rivers. Okay, is rivers. Here's the major rivers of Florida, and if you can't read them, they are the Apalachicola, the Suwannee, and the St. Johns, and none of them directly affect Apalachee Bay. And I've got two different pointers now. The intermediate-sized river, there is in fact one that comes in on the western side of Apalachee Bay, and that is the Apalachee, as you can see. I hope you can see. And then when you throw in all of the other rivers and streams, there's about a dozen that flow into Apalachee Bay and provide fresh water, but again, not enough to make it an estuary. And some of these will come up. Probably one that will certainly come up is the Osceola, which is right above the sea in Apalachee there. So you'll hear a lot about the Osceola River today. But about a dozen small streams flow into Apalachee Bay. The point about rivers is that the important resources at the mouths of coastal rivers, estuaries especially, lagoons, barrier islands, wetlands, they're all there because of sea level, as you heard from Tom Cronin. Sea level certainly pops up and down with the glaciers advancing and retreating, and we're at one of the pop-up spots in geologic time right now. And where sea level is determines where these coastal resources are and where they're available to native populations. The second aspect is springs, and this is a map of the named springs of Florida. There's 330 of them. 32 of them are major springs, first magnitude springs, meaning 100 cubic feet per second or more. And when you blow up the middle there, here's where we are. And so these are the springs of those small rivers that flow into Apalachee Bay. And again, the ones that will probably come up today are these down on the lower Osceola. And Peter Kleinhens yesterday at the reception mentioned that there's another one that should be on this map right about there, I think, that's recently been discovered on the Osceola. The third aspect of the natural system is us. So this is a coastal population map showing density. It shows where we live. for the U.S. First. So this is the latest census showing that 40% of us live at the coast, meaning in the coastal zone. And for Florida, that number is even more skewed. For Florida, 75% of us live at the coast, with the main exception being where we live now, which is Orlando. But other than that, most of the big population centers are coastal in Florida. It's hard to find a map like this for prehistory, and I really looked in the literature to try and add to this slide, but this is about one of the few that I found. This is a map put together by Peter Wood in 2006, based on Spanish histories from the time of first contact around the 15, the date, you can see the dates on some of these Spanish explorations, 1530s, in that area, showing where the concentrations of Native Americans were when the first Europeans showed up. So they weren't actually coastal, but I think you can see they lived on rivers that gave them easy access to coastal resources. Interesting fun fact. So here's, right here in the dashed lines, is De Soto's path starting in Tampa Bay in 1539. He made his way through the forests and got to Tallahassee for the winter of 1539, 1540, and camped there. And we used to live 2 blocks away from what was discovered to be that campsite. Jim Dunbar actually had his office right on that site at the Bureau of Archaeological Research, shortly after 1539. This is a sea level curve. So you saw one version of a Chesapeake Bay sea level curve a few minutes ago. This is a global sea level curve based on ice volume. It was put together about 10, 15 years ago. And it's one of the better ones, but they all look pretty much the same in terms of structure. So this one shows 2 important aspects. One is the last glacial maximum. So you'll hear a lot about that today. Normally it's shown at about 120 meters below present and at about 20,000 years ago. So that's when the glaciers kind of bottomed out. It was the apex of the last glaciation. And another important aspect of these curves, as you heard from Tom Cronin, is the rate at which sea level rises during these pulses. So there's, on this one you can see maybe 3 or 4 pulses of rapid rise, that is steep slope on the curve, during which time sea level is rising fast in terms of meters, many meters per century, versus today when it's rising at about 33 centimeters per century at an average rate. And then there's these short, relatively short, maybe 1,000-year-long periods of what we call still stands, when sea level pauses and maybe even goes down on this curve. So that's a global sea level curve. I put this in, I added this to the map just to show that Florida Man, the person that gets all the headlines here in Florida, and Florida Woman, I guess, too, has been around for perhaps 14,000 years. The archaeologists may differ somewhat on that, but something like that, which means that Florida Man has been here since sea level has been rising vertically as much as 90 meters and moving the shorelines horizontally in places, as much as 100 kilometers, especially on the Gulf side. So that's what I want to focus on. I want to look at what the effect of all those vertical and horizontal changes has been on Florida. This is a sea level curve that I put together with Jim Basile when he was at the Florida Geological Survey. There's been different versions of this. This is a very cleaned up version, but I left out a lot of the detail so that we could kind of focus on some specifics. So what you see in this curve, this kind of curve is different from the one you just saw. So the one you just saw is based on ice volume. This is based on actual artifacts found out on the continental shelf. By artifacts, I mean things like oysters, things that grow at sea level and can be carbon dated. Oysters, freshwater peat, corals, things like that. So we had 350 that we collected from both our research and also mostly from the literature. So what you see in a curve like this is that sea level bottomed out in the Gulf at about 120 meters 20,000 years ago. So the shoreline 20,000 years ago would have looked something like this. And another aspect of this kind of this detail in the sea level history of the Gulf is that there are at least 5 of these excursions, these major, so I've put that in yellow, showing that these periods when sea level was rising preternaturally rapidly. So here we are today with sea level, as you saw in the Chesapeake Bay record, sea level not really changing very much the past 6,000 years, but there are periods here when sea level was rising. Here's some rates, just some average rates. And if you can't read this in the back, I noticed that the lettering is pretty small on the screen, but the rates here are on the order of 40, 45, 25, 20 millimeters per year. Whereas today, the satellite record, like you just saw from the Chesapeake Bay, going back to 1993, says that sea level's been rising, at least since then, at about 3.2 millimeters per year. So it's an order of magnitude greater rates of rise during some of these pulses of sea level. We call these pulses, here's the abbreviation here, meltwater pulse. We call them pulses because these were times when real cataclysms came down some of the water courses, down the Mississippi, down the St. Lawrence Seaway, down the Columbia River, and just, the equivalent of many years' worth of Amazon River flow just within the space of probably months. And so sea level rose at horrendous rates. So, and the important thing is that during times like that, coastal resources really don't develop. You don't really get well-developed estuaries, if at all, or well-developed barrier islands or deltas. So it's only during these pauses, of which we're in a long one right now, but there's a few others, as you can see, when shorelines develop. So I want to look at the possibilities for that. So what I've outlined here are the 4 pauses, well, 5 including the modern one, during which time humans have been around and during which time shorelines may and probably did develop. So the first one, and here's where they would be. So these would be the 4 late Pleistocene, Holocene shorelines in the Gulf. First one would have been going backwards in time, the 12-meter shoreline. So at 12 meters water depth. An example of that is maybe right here in Apalachee Bay. So in another study, Michael Fott, an archaeologist at FSU at the time, and I put together, we collected some seismic data. So using acoustic profiling, relatively low frequency sound, and pulsing it down through the bottom, you can see in the subsurface what the bottom used to look like before it filled in. So these are what we were looking for was these paleo channels of these rivers. There's the Osceola, and the St. Mark's is over here. The Apalachee comes in off the slide. So what we were able to do from that seismic data is to put together a river map, but these were paleo rivers. These were the rivers probably about 8,000 years ago. And so the system, which really is the Paleo-Ochlockonese system, these being tributaries of the Ochlockonee at the time, looks something like this. And we superimposed on it some of the sites that existed. These are early human sites at the time. The oldest one being Ray Hole Spring. And I bring that up because that sits right at about 11.5 meters. So Ray Hole Spring, which was a flowing spring at the time, and which there's evidence that humans were there. There's lithic debitage. Ray Hole Spring may represent that pause at 12 meters, which is about 8,000 years ago. The 12-meter shoreline. The next one down is the 25-meter shoreline, and you can see where that is. A possible remnant of that, this is from another study that I did with Alan Niederode of the URS Corporation, where we were looking at the same kind of seismic data. This was our data for paleo channels of the Ochlockonee and other smaller rivers, plus the Apalachicola. This is ours. And then we grabbed some data from oil companies, actually, for West Florida, similar kind of data, and we plotted out the paths of these coastal rivers. And it turned out that they put in the bathymetry. Turned out that they bottomed out between 20 and 30 meters, so about 25 meters or so. This is 20 meters, that's 30 meters. It is where most of them seem to bottom out. So we think that those rivers were well developed at a time when the 25-meter shoreline was extant. So that would have been about 9,000 years ago during this pause between these two pulses. 36-meter shoreline, the best example that I can present of that, because the data get more sparse as you get further offshore because it's harder and harder to do science in deeper water. So 36 meters is 120, 140 feet. It's kind of beyond scuba, but a 36-meter shoreline might be represented by the Florida middle ground. So a lot of us, anybody who's a fisherman knows about the middle ground. So middle ground is a hard ground in 36 meters. It's a reef, fossil reef, but the reef itself has been examined by Mallinson, Dave Mallinson at USF, and what they found was that underneath the reef, it's actually based on a former shoal. So it was a high point, which they identified as a delta. So it was a delta from this time right here. We call this actually the Younger Dryas. It's a time. This is a pause between these two pulses. The Younger Dryas between 11 and 12,000 was a pause in the sea level record. And you can see it in all the global records as well, but especially in the Gulf of Mexico record. So they identified that as possibly a shoreline that persisted during that 1,000 years or so of the Younger Dryas. So that's the 36-meter shoreline. And the last one is, I didn't put a question mark on this one because this one really has been identified as a shoreline, even though it's the furthest offshore. The 64-meter shoreline is represented by the, again, this is a study by Gardner et al. In 2005, led by the USGS. They call these shelf edge paleo delta barrier systems. So this is definitely a shoreline. They found about actually 6 former paleo deltas, delta barrier systems out here. We can look at one. So this would have been at about 14,000 years. And so potentially Florida man could have visited out there too. So this is what they look like. So this is based on high resolution, not acoustic profiling, not deep profiling, but profiling of the actual seafloor. So this is the topography of the seafloor. It's called, it's basically sonar. It's multi-beam sonar. So here's what one of them looks like. This actually, the one that I'll show you, so they had all these in their publication, but the one that I'll show you is this one because it's at the same latitude as an equivalent system that we'll look at onshore, the Apalachicola Barrier Delta system. So here's what it looks like. So this is in 64 meters of water. This is what the seafloor actually looks like. And you can draw a profile across it, and it looks like that. And I've put question marks on this. I did this profile in a plotter, but I put question marks on this because nobody's actually been there. I mean, they went out there and collected sediment samples and so on, and they speculated about the age and about the origin. And they basically said it was a delta, but it appears to be an entire barrier, lagoon, wetland, beach ridge plain. These are just in a perfect shape of beach ridges. The scale here is, I think full scale is about 4 or 5 meters, and the scale horizontally is about 5 kilometers. It's basically the same as what you find onshore. So here's the equivalent onshore, and you can do the same thing with the Apalachicola barriers. Here's St. Joe Bay, if a lot of us are familiar with that. There's the Apalachicola River and Delta. This is the well-developed beach ridge plain over there. Here's the lagoon and wetland, and a cross-section there looks essentially the same as the one you find offshore. So it's a modern equivalent of that system that sits at about 64 meters water depth and is about 14,000 years old. So anyway, all of these shorelines could have been, and some of them have been, the habitats of early humans here. I want to finish up, so there's the two side by side. I want to finish up, conclude with this. So this is a report that came out just 3 weeks ago. So some people might have seen it, by NOAA. So this is the latest in now a long line of reports on climate change, but this one actually refers to specific areas in terms of sea level change. So they actually have data here from the models, the same models that Tom Cronin just talked about. The IPCC uses them as well, models for global sea level change, and they apply it on a regional basis. So what I'll show you is the data from the eastern Gulf of Mexico. So for the eastern Gulf, the projection in this report is that by 2050, sea level will have risen 1.5 feet, about, you can see it here, about half a meter, and by 2100, as much as 5.5 feet. And that's they say that's the best estimate. In other words, they're saying that this curve in the orange is the most likely estimate. This, just as you saw with Tom Cronin's IPCC plots, goes from best case to worst case. Best case would be, we stop burning fossil fuels immediately, and worst case is we burn them all. But yeah, by 2100, this is what 5 feet looks like for Florida. The red contour is 5 feet. So, goodbye Miami, and goodbye most of southern Louisiana. So by 2100, at 5.5 feet, what happens is, as Tom Cronin mentioned, the rate of sea level rise increases exponentially. So as I mentioned today, the rate that we've seen with the satellite data is about 3.2 millimeters per year. At the assumed level of sea level by 2050, the rate will be about 17 millimeters per year, and at the assumed level by 2100 is 31 millimeters per year, an order of magnitude faster than today's rate. So let's hope that we get something more like the best case than the worst case. All right, thank you very much.
The name of the research scientist at USF that you mentioned who's studied the middle grounds?
Yeah, David Mallinson.
How do you spell his name again?
Mallinson.
Is he over at School of Marine Science
Yes.
in St. Pete?
Yes.
Okay. How long has he been there?
Oh, a long time, I think. Yeah.
Okay. That's really the major question that I had.
Yeah, I can give you the reference later if you want. Yeah.
Thank you. I appreciate that. Thank you.
Could I ask a question? I can't raise my hand for some reason.
Yes.
Yes.
That was a great talk, Joe. There's so much offshore archaeological data I didn't know about. Is there ongoing work now offshore on some of the older shorelines and native people populations?
Yeah, probably Jim Dunbar would be a better person to ask about that. The work that I did with him, especially at Rayhole, that was more than 10 years ago, about 15 years ago. So I can't directly answer that, but when Jim comes up, he'd be a better person to answer, Tom.
Okay, thank you.
I'm Andy Hemmings, later speakers, and I'm an archaeologist here in Florida. There's some smaller projects gearing back up again after the world of COVID off the Econfina. Some of our stuff nearer shore, first within Florida waters off the Oscilla. And there's another research group with Mike Fott, Dave Thillman, Morgan Smith, and Sean Joy that are getting a little bit farther offshore and looking at deeper and deeper sites. And then out of Aussie, everything's been slow for a number of years right now.
Yeah.
Okay, thanks.
I'm here.
Hi, Michael.
Hi, Michael. How are you?
I'm good. I'm in Arizona.
Okay.
Hey,
Joe,
but the issue is that there's currently people on the offshore doing research in Apalachee Bay. I don't know how far out. I don't think they're going much more than about 9 miles. It's a DHR grant. Morgan Smith and Sean Joy with the Archaeological Research Cooperative are testing the HALD methods, the human altered lithic detection method, and it seems to be working pretty good. So I just wanted to say that, yeah, people are out there now. It's great.
Thank you.